Now, uh, we know that whenever Coulomb has said that whenever there is some particular charge, when there is a charge present, static charge, around this charge there will be some force. There will be some force around this charge. We know that. That's what Coulomb's law says. Coulomb has already given us. Okay. So Coulomb has already told us that whenever there is a charge, right, around this charge there will be some force present. Okay, and you can calculate the force, right? So this is the simplest method. But now, whenever there is a point charge, there are some limitations of Coulomb's law. Coulomb's law cannot be applied in all cases, right? So Coulomb's law will not give you exactly or accurately the value, right? In all cases, there are certain limitations. Okay, so there are certain limitations for applying the Coulomb's law. What are those limitations? So if you see the limitations, the first there are okay, right. So there are two limitations. There are two main limitations of Coulomb's law. So the first limitation is the Coulomb's law will only work well whenever we talk about point charges. Okay. So the force expression or the electric field intensity that we calculated, this will be well and good if we are calculating this formula for point charges. Okay. So for line charges and for other kind of charges like spherical charges, etc., this expression of whatever we calculate, electric field intensity E bar or the force, will not work good. Okay, so that is one problem, right? So this is the first limitation. The first limitation of Coulomb's law is you can calculate the electric field intensity or force due to any kind of charge using Coulomb's law. Okay, but the point is this, whatever the electric field intensity you calculate or whatever the force you calculate, the expression of force, this will work very well only for, that is, it will give you accurate results only for point charges. For other kind of charges like for a line charge or for a volume charge or for a surface charge, whatever the electric field intensity or whatever the force you calculate will not give you accurate results. Okay, so that is a problem with Coulomb's law. Okay, similarly the second point or the second problem with Coulomb's law is, so whenever there is a combination of charges, okay, or whenever you don't know what kind of charge is exactly present, okay, whenever there is a combination, let's say a point charge is there, a line charge is there, or a surface charge is there, for example. Okay, let us assume that there are some kind of charges, okay, a line charge or a surface charge or a volume charge, like this. Okay, different types of charges are there. So for all these kind of the all the combination of these charges, okay, when you combine these charges, even though you can calculate them, individually, you can calculate them individually, and you can use the superposition principle and add them up all, but that will not give you accurate results, right? So because the direction will be different from point charge, the field direction will be different, the line charge field direction will be different, and volume charge field direction will be different. So field direction will be different for line charge, for point charge, and surface charge. So therefore, right, when I do this, I will not get the accurate value of electric field intensity. So these are the two main drawbacks of the Coulomb's law, right? So therefore we cannot apply Coulomb's law in all, right, practical cases. There are limitations of Coulomb's law, right? So there are two main limitations. What are the two main limitations? First limitation is the Coulomb's law will be accurate only for point charges. The calculations done by Coulomb's law will be accurate only for point charges. For a line charge and for surface charges, the whatever the value of E bar or a force you calculate will not be accurate. That is the first point. Second point is, right, so Coulomb's law, whenever there is a combination of different charges like a point charge, a line charge, a surface charge, etc., when all such of them are present in together, right, in as a combination, then in such cases it is not possible to calculate the electric field intensity accurately. Okay, so there the Coulombs law fail. Okay. So in such cases, how to calculate electric field intensity? Okay. So firstly, as I said, electrostatics means you need to calculate, or here what we are going to study, we are going to study how electric force, okay, electric force or electric field intensity is to be calculated. That's it. The unit mottum, what we are going to study is, we will be studying how we can calculate electric field intensity due to different charges. Okay, right? Simplest method to calculate them is Coulombs law. Okay, Coulombs law is the simplest method by which you can calculate the electric field intensity. But Coulombs law cannot be applied or cannot give you accurate results in all cases. It fails. It fails in two cases. What are the two cases? First thing is, whenever there is a other than point charge, then whatever the electric field intensity you calculate will not be accurate. Okay, that is the first point. Second point is, whenever there is a combination of charges, let's say when there is a line charge, there is a surface charge, there is a volume charge. In such cases, also the Coulombs law does not work properly. Okay, right. Now, how to do that? Okay, so therefore, we go for the second method. The second method for calculating, right, the electric field intensity. So the second method is based on Gauss law. But before studying Gauss law, right, the second method will be based on Gauss law. What is this Gauss law? We'll study later. But before that, we need to study a concept called as flux, electric flux. Okay, electric flux and electric flux lines. Okay, flux density. Flux and flux density. So what is this flux and what is this flux density? We will study. I hope that you are noting down, because it will be very useful when you're noting it runningly, right? Running notes. Okay. Even though I will provide the notes later on, but it will be better if you note down. Okay. Right. So first thing is, what is flux? Okay. So as we have already discussed that whenever there is a charge, right? Whenever there is a charge particle, whenever there is a charge at right rest, okay? Whenever there is a static charge, whenever there is a static charge, as per the Coulombs law, there will be some force around this charge, okay? And the region where this force is felt, and the region wherever you can feel the force, is what we call it as, right, the field, electric field around the region, right? So this is what Coulombs law has done. Okay, right. Now later on, for the slight improvisation of this concept, is the next is flux. So Faraday, right, from Coulomb, he has taken over and he has conducted an experiment, right? Faraday's experiment. What is this experiment is, he has put a positive charge on one side and a negative charge on like this. He has taken a combination of a positive charge and a negative charge like this, a positive and a negative charges. Okay. And he has taken a one Coulomb positive test charge, that is unit test charge. Okay. Unit positive test charge. So he has taken a unit positive test charge and he placed this test charge near this particular combination. Okay, so I'm repeating it again. So firstly, what he has done is, he has taken a a combination of positive and negative charge placed together. This is what we call it as dipole. We will study that later. Okay, so a positive test charge, a positive charge is there, a negative charge is there, and they are placed very closely to each other. Okay. And what he has done is, he has taken a 1 Coulomb, right, plus 1 Coulomb, that is a unit positive test charge. Okay, a unit positive test charge is taken and he placed it near in this region, in the vicinity of this charges. Okay, so we said that whenever there is a charges at rest, there will be some force. Okay, so what he has observed, that this, whatever the positive test charge is there, so this will repel this and this will attract this. Okay, so positive will repel and a positive negative will attract. Okay, clear. So this, whenever this is repelling, right, because of the repulsion and because of this attraction, this unit positive charge, it is moving. It's not linearly moving, it is moving in an elliptical manner around like this. Okay, so what we get is, so this is my positive charge and this is negative charge. So he has observed that, right, this unit test charge, whatever you place, will be moving elliptically around the right charged body from positive to negative way. Okay, so from positive to negative way, right? So because of this, okay, positive to negative way, right? So he has observed that this unit test charge, whatever you place, it will move in a particular elliptical fashion. Okay, so Faraday named this whatever imaginary lines in which this unit test charge is moving, so he named them as flux lines. He named them as flux lines. Okay, so what we uh, what we are saying is, so whenever there is a positive charge or whenever there is a charge at rest, whenever there is some q, as per Coulombs law, there will be force. Okay, now what Faraday has said that this force, whatever it is acting, whatever it is there, that force will be present or will be right surrounding the charges in the form of right lines, flux lines. Okay, so in the form of imaginary lines, right? And a force anedi, it will be existing in the form of lines. Okay, so these lines, these imaginary lines that are present around the charges are called as flux lines. వీటిని ఏమంటున్నాం అంటే flux lines అంటున్నాం. Okay, so flux lines అంటాం వీటిని, right? So these lines are called as flux lines. Okay, now the total number of lines that are produced, the total number of force lines that are produced by a charged body is called as, right? For example, if I have a charge q, so the total number of lines that it produces, right, the total number of force lines it produces, right, is called as the flux of the material, right? Psi, represented by psi. Okay, so you call this that is the total number of flux lines produced by a charge particle is called as the flux of the charge particle. Okay, understood? So I'm repeating again, right? So the force that is, or the electric force or magnetic force, whatever it is, right? The force that is created here, the electric force that we have calculated or that is assumed to be present, right? This will be present or this will be existing in the form of lines, right? These lines are called as flux lines. Okay, right? And the total number of flux lines that are produced by a particular charge particle is called as the flux of the charge. Okay, so for example, if I have a charge, let's say, then it produces 1,000 flux lines over in a closed surface, in a particular boundary, right? So then the flux of this charge particle inside this boundary is 1,000. Okay, it is a scalar quantity, right? The point observed to be observed is this is a scalar quantity. Psi is a scalar quantity. Flux is a scalar quantity. Okay, so I think clear, understood, right? So Coulomb's law, Coulomb has stated that whenever there is a charge particle, there will be force, right? Now what Faraday has said that if this force, whatever it is there, it will be existing in the form of like lines, right? These lines are called as flux lines. Okay, these lines are called as flux lines, and the total number of flux lines that are produced by a particular charge particle is called as the flux of the right charge particle. Okay, so we call it as the flux. It is represented by psi. Okay, right? But this psi is a scalar. As I said, this psi is a scalar. But whereas our field intensity, that is electric field intensity or force, has to be a vector, right? So we cannot calculate a vector from a scalar. How is it possible to get a scalar vector from a scalar? It's not possible. So for calculating electric field intensity, right, we should convert this scalar quantity into some vector quantity, right? So am I clear, right? So that is the flux that we are saying is a number. Basically it is a number. It represents the number of flux lines that are produced by a charge particle. This is a scalar quantity, right? Whereas what we intend to calculate, force or electric field intensity, F bar or E bar, F bar or E bar are basically vectors. Okay, so it is not possible to calculate a vector from a scalar. Is it possible? No, it is not possible. So therefore we need to, right, give direction to this quantity, right, or convert this quantity into a vector. Okay, from a scalar we need to convert it into a vector. How to do that? So just what we do is, okay, so we will consider, right, again let's say, again we'll start from the beginning. So there is a charge particle, right? Around this charge particle, there will be force, right? And that force will be existing in the form of flux, right? Lines. These lines are called as flux lines. Okay. Now what I do is, so I will, let us say this is a positive charge and there is a negative charge, minus q. So we always, right, have to remember that the flux lines will start at positive charge. Okay. They will always start at a positive charge and they will always end at negative charge. Okay. So for example, if there is no negative charge, then only positive charge. That means this flux lines, they will be traveling to infinity. They will end at infinity. Okay. So if the flux line, if there is only positive charge, let us say there is no negative charge close. That means these lines are traveling to infinity. Okay. So the negative charge is assumed to be present at infinity. Okay. Similarly, if only negative charge is there, right? No positive charge, then also we assume that the flux lines are, right, originated at a particular right infinity, a positive charge at infinity, and they are, right, sinking at the minus q, that is, right, negative charge. Okay. So positive charge aithe, right, q దగ్గర originate అయ్యి they will go travel to infinity. Negative charge aithe, right, infinity దగ్గర originate అయ్యి, right, they will end at minus q. Okay, clear with this? So these are the flux lines we have to assume. And in general, if there are positive charge and negative charge, then they will start at plus q and they will end at minus q. Okay, right. These are the two important properties we have to remember. All right. Now let us assuming that there are flux lines, okay, starting at plus q and ending at minus q. Okay, so flux lines have started at plus q and they have ended at minus q. So, right, like this, let us assume there are something like this. Now, right, to convert this into vector quantity, what I am doing is I am considering a surface normal to this flux lines. Okay, for example, these are the flux lines. So what I am doing is I am considering a surface normally like this. Okay, like this, right? This is the normal. Normal means they are passing through it, right, in a 0 degrees, 0 angle like this. Okay, so I'm considering a normal surface. Okay, so a surface normal to the flux lines, right? Okay, normal to the flux lines, uh, normal to the flux lines. And right now what I'm doing is I'm calculating the number of lines passing through this surface in the normal direction, not in all directions. So that is like this. So the flux, this is the normal surface, these are the flux lines. Okay, so I am going to calculate how many number of lines are passing through this surface, right, for passing through this surface in the normal direction. Okay, in the direction normal. So, right, okay, so the number of flux lines that are passing, the number of flux lines that are passing through a particular, right, area in the normal direction will is what we call it as flux density, right? So flux density, which is represented by d bar, is a vector. Okay, flux density is a d bar, which is represented by d bar, is a vector. Okay, what this vector gives you, or what this vector tells you, is how many number of flux lines are passing, right, passing through a surface in the normal direction, right, to it. Okay, so generally we write a d bar as, right, psi by a or s, that is area, right, surface area of this object. Okay, okay, how many number of lines are passing, right? Okay, number of lines passing to the surface area of the object, and this is the magnitude, right? It also needs direction. So what is the direction? Normal direction. So an bar represents the direction normal, right, normal direction to the surface. Okay, right, am I clear, ma? So, right, what we are saying, whenever there is a charge particle, the charge particle produces force. Okay, the charge particle produces force. This force will exist in the form of lines. Such lines are called as flux lines. Okay, point 3, flux lines. These flux lines, they will start at plus q, positive charge, and they will end at negative charge. Okay, the number of flux lines produced by a particular charge is called as the, right, flux of the material, right, psi. Okay, right? The psi is basically a scalar quantity. It is not a vector. It's a scalar quantity. It will tell you the total number of lines that are passing through a particular, right, closed surface. Okay, but we need a vector. So how to do that? So convert the scalar into vector, right? How am I converting? Right, I'm taking a normal surface, a rectangular surface, or a closed surface, anything. It can be a rectangular or it can be any closed object. Okay, I'm considering a closed object and I'm placing this closed object, right, normal to the, flux lines. Okay, right, I'm placing the closed object inside the flux lines. Okay, and then what I'm doing, I'm calculating the number of lines that are passing through this object, right, that are passing through this body in the normal direction. Okay, so I'm calculating the number of lines that are coming out of the body, right? So that will give me, right, what we call it as flux density, right? So population density means total population to total area. Same thing here also, total flux lines to the total area that is passing through this object. But only thing is we have to give direction. What is this? So the number of lines that you should consider, they should be only considered in normal direction. We cannot consider a line going out like this or like this or like this. It has to go, right, in the normal direction, radially outward from the body. Okay, so such kind of things are what we call, this is called as flux density. Okay, I think I am clear, right? I hope I am clear. Okay, so flux and flux density, right? We have covered two things. Okay, so flux is generally represented by psi, right? So psi represents flux. Okay, right? And flux density is given by d bar. So we write d bar as psi by, right, a or s. I'm using s, right? S is the surface area, right? And direction will be an bar, normal direction to the surface. Okay, right? This is the thing. Now similarly, if I want to calculate psi from this, right, what I do, psi is equal to, right, so multiply d bar, integrate it, and with respect to this, so this will give me the total flux, right? If I know the flux density, I can calculate the total flux using this formula, right? Integrate the d bar over the entire surface. Okay, so if I want to know what is the total flux that is present inside a closed surface or an area, then I can do it using this formula. Okay, so I think these three things are clear, right? Flux density, and how we can calculate. Okay, right. So is it any doubts till now? Just 2 minutes. So any doubts or any thing you want clarity? Am I clear first? So if you have any doubts, you can just ask in the chat box. I'm waiting for your doubts. Otherwise, I'll go to the next topic. Any doubts? Any doubts? Any doubts? Nothing? Okay. One person, yes. Clear, sir. No, sir. Continue, sir. Okay, right. So let us go to the next topic, right? Then. So now, after knowing what is flux and flux density, let us go to the next concept, right? That is what we want actually is the Gauss law, right? So what does this Gauss law says, right? So it's a simple thing, right? Gauss law. What Gauss law or what Gauss has said, that is, so for example, if I have, let's say, a charge, right? Okay, Q. This is a charge. So I don't know what type of charge it is. Okay, so I don't know what type of charge it is, or this charge can be a point charge or a line charge or a surface charge, anything, right? Okay, or it can be a combination of all these things also. Okay, సో అది లైన్ చార్జ్ కావచ్చు, పాయింట్ ఇంకా కాంబినేషన్ కూడా అవ్వచ్చు. ఓకే, సో లెట్ us assume, right? Now if I take a closed surface around this, right? If I take a closed surface around this, and if this surface is a Gaussian surface, what is this Gaussian surface? I'll tell you later. Okay, so we study about it's not a such a strange thing. what is that? We'll see later. Okay, so if I take a closed surface around this charge, okay, if I take a closed surface around this charge, right, then right, closed surface around this charge, then the number of, right, lines or the flux, okay, the flux that will be coming out, the flux that will be coming out will be equal or will be proportional to the charge, okay, right, and you can take the magnitude of the charge and the magnitude of the flux as same, okay, ante simple thing, right? So manaku some charge, there is some charge present there, right? That charge can be anything, it can be a point or line or something, whatever it is, no problem, right? If I take a closed surface around this charge, right, if I take a closed surface around this charge, right, and calculate the flux in that particular closed charge, then what Gauss law, what Gauss says is this flux will be proportional to q. Obviously we know that the flux will be, that means if more is the charge, more number of flux lines will be producing, less is the charge, less number of lines will be producing. So what he says that you can take this proportionality and you can make them equal, that is the charge present inside a particular object will be equal to the number of flux lines that are producing from the charge. Okay, this is the most important thing, right, or what we call it as Gauss law, right? So Gauss law em cheptundante, meeku oka charge particle unte, right, charged body edaina unte, then the number of flux lines that are coming out will be equal to the charge, right? So you don't need to know what charge is present, right? If you know, if you can calculate the psi value, if you can calculate the flux, right, coming out of this particular charge, right, అంటే నాకు I don't need to know what is there, the charge ఇందులో ఏదో ఉంది, there is some kind of charge, whatever may be it, whatever it might be. Coulombs law ద్వారా if I want to find out, let's say if I want to find out electric field intensity at this point, I should know what is this charge, what is the value of q, right? Okay, q value ఏంటో నాకు తెలియాలి, is it right? Okay, we should know what is the value of q, then only we will be able to calculate electric field intensity at a particular point. If we don't know the value of q, it is not possible to find out the value of E bar. Okay, so that's a problem, right? You know, you right, and also if the value of q or whatever the value of q that you are taking, if it is a combination, right, let's say line charge, surface charge, etc etc, okay, then it is failing. So for that, what is this Gauss has done is, so whatever might be this, right, q might be anything, okay, just take a closed surface around this q, right? ఈ q చుట్టూ ఒక closed surface తీసుకోండి, right? You calculate psi. Psi means what? The flux coming out of this particular charged body, or you calculate d bar, whatever it is convenient. You can calculate, you can take a normal surface, you can calculate flux density, or you can calculate the flux, the total flux that is coming out of the this entire object. Okay, so in such case, right, if you know what is the what exactly what is the flux coming out of this q, then I can calculate, right, or I can equate this flux to the charge, right? Psi will be, or q will be taken as psi itself. Okay, so this flux, the number of flux lines or the flux produced will be, right, almost equal to the charge, right? So if you can calculate psi, that will be equal to the charge, means అంటే mathematical గా ఈక్వల్ అంతే, రైట్? ఇదేమో q is measured in coulombs, ఇదేమో number of lines, ఆ రెండు ఎలా ఈక్వల్ సార్ అని అడగొచ్చు, రైట్? How can we say those two are equal? అంటే mathematically it is equal, it is almost equal, and we, in place of q, we can use psi to do all the calculations. That's what the meaning is. Okay, understood? So right, this represents number of lines, this represents coulombs, number of coulombs, or the charge. How are these two equal means? So what we mean to say is the flux lines, right, in place of q, you can use the value of psi to calculate, to do all the calculations, so that's what Gauss law says. Okay, right, I hope I'm clear, but I'll repeat it again. So what Gauss law says is simple statement. It says that psi is equal to q. Psi is equal to q. What is psi? Flux. what is q? Charge. Okay, ante oka charge chuttu if I take a closed surface, then right, then the number of flux lines or the flux of the charge will be same as that of the charge itself. Okay, so psi will be equal to q, right? అర్థమైందమ్మా? So I think I'm clear. I hope you understood this. Okay, so but the simple point is we don't need to understand all these things. The simplest thing is we have to understand, or we have to thing is where or how to use this is, so we have to understand that wherever there is q, right, wherever there is charge, we can replace that with psi. Okay, we can replace that with psi. That is, if I know the flux lines, I'll take a Gaussian surface, right, around a particular charge. I'll calculate the number of flux lines or the flux density at that particular point, at a point. Okay, then if I know this value, I can calculate all the E bar calculations or F bar calculations. Okay, so I think I'm clear, right? So the important relation that we have to use, or we have to observe, is psi is equal to q, right? Okay, so if this is a point charge, this is the case, psi is equal to q. If it is a line charge, right, we know that q can be written as rho l dl, right? Rho l dl is the expression for line charge, so psi will be equal to rho l dl for line charge. For surface charge, it will be rho s ds. Okay, for volume charge, it will be rho v dv. Okay, so the expression for psi for different charges, for point charge, it is, we write simply it as psi is equal to q, right? For line charge, it is rho l dl. For surface charge, rho s ds. And for volume charge, rho v dv. Okay, so this is the expression for psi that we have to remember. Okay, right. Now so this is the Gauss law, the simplest law, right? It's a simple one. So it says that the charge is equal to the flux coming out of the closed surface. Now we discussed that whenever you want to apply a Gauss law, right, or whenever we want to use Gauss law, we have to study something called as Gaussian surface. What is a Gaussian surface, right? What is Gaussian surface? So it has to satisfy two important conditions. A Gaussian surface is a surface which has to satisfy two important conditions. What are the two important conditions? First condition is it should be a closed surface. It should be a closed surface that can be regular or irregular. Okay, అంటే అది క్లోజ్డ్ సర్ఫేస్ అవ్వాలి, రెగ్యులర్ అవ్వచ్చు, ఇర్రెగ్యులర్ అవ్వచ్చు. రెగ్యులర్ మీన్స్ లైక్ ఫర్ ఎగ్జాంపుల్ దిస్ ఇస్ అ circle which is regular like this. If I draw something like this, this is irregular. Okay, so we cannot define it with mathematical equation. This can be defined it with mathematical equations. Okay, so this is a regular surface, this is a irregular surface. Okay, so first condition is the surface that we take should be closed in nature. It can be regular or it can be irregular. The second condition is the most important condition is, right, this closed surface, right, should have or should be such that the normal vector of this surface with the field will be either, right, normal or tangential. Okay, ante ఈ closed surface, whatever the closed surface that we take, this should be, right, placed, or this can be called as a Gaussian surface if it right, if it is perfectly lying either normally to the field lines or tangentially to the field lines, like this or like this. Okay, this is what we call it as normal, right? So this way what we call it as tangential. అంటే ఫీల్డ్ అనేది ఈ పర్టికులర్ సర్ఫేస్ నుంచి, ఈ పర్టికులర్ సర్ఫేస్ యొక్క స్ట్రక్చర్ అనేది ఎలా ఉండాలి అంటే, ఫీల్డ్ అనేది ఎయిదర్ నార్మల్ గా అన్నా పాస్ అవ్వాలి, లేకపోతే టాంజెన్షియల్ గా పాస్ అవ్వాలి. ఓకే, అంటే 0 degrees తో అన్నా పాస్ అవ్వాలి, లేదా 90 degrees తో అన్నా పాస్ అవ్వాలి. ఇలా మధ్యలో లైక్ దిస్, ఇట్ కెనాట్, you cannot, the field cannot leave the plane or enter the surface like this. ఓకే, అంటే దాని యొక్క స్ట్రక్చర్, ఈ ఏదైతే మనం గాసియన్ సర్ఫేస్ తీసుకుంటున్నామో ఈ సర్ఫేస్ యొక్క స్ట్రక్చర్ ఎలా ఉండాలంటే, అంటే ఆ సర్ఫేసెస్ ఎలాంటివి చూస్ చేసుకోవాలి అంటే మనము, రైట్, సో ది surface should pass the field lines or the flux lines only in this particular direction. E particular direction lo ante like this or this, like this way. So either with 0 degrees or with 90 degrees. It cannot pass with an arbitrary angle like this. Okay, arbitrary angle తో పాస్ అవడానికి లేదన్నమాట, రైట్? సో ఇది మనము, దిస్ ఇస్ వాట్ వి కాల్ ఇట్ as Gaussian surface. ఇది ఏంటంటే కొంచెం మనం కాంప్లికేటెడ్ అనిపించవచ్చు కానీ బట్ ఇట్స్ వెరీ సింపుల్. అంటే ఆల్మోస్ట్ all surfaces satisfy this condition. Okay, like circle, sphere, rectangle, triangle, right? All these kind of surfaces, they satisfy this condition. So any regular object, right, any regular object, okay, with at least one tangent or one normal is what we call it as a Gaussian surface. Okay, so don't worry about this. This is a simple thing, right? So what is a Gaussian surface means? It has to satisfy two conditions. First condition is it should be closed. It should be a closed surface. It cannot be an open surface like this. You cannot consider a surface like this as open, right? Like as a Gaussian surface. Okay, this is a half arc. So you cannot consider this half arc as a Gaussian surface, right? So like this. Okay, so it has to be closed. Second is this Gaussian surface should be in such a way that the field will be either leaving normally or tangentially from it. Okay, you cannot leave with an arbitrary angle, right? So that's what we call it as Gaussian surface. Okay, don't worry about too much about this. This is a simple thing, right? Now let us come to the most important thing. The problems will be asked, right? In this, from this part, the question will be asked as a problem on Gauss law, right? అంటే మనకి ఈ పార్ట్ లో మనకు మోస్ట్ ఇంపార్టెంట్ టాపిక్స్ రెండు ఉన్నాయి. ఒకటి ఏంటంటే గాస్ లా యూస్ చేసి హౌ టు క్యాలిక్యులేట్ ద ఈ బార్ ఆర్ ఎలక్ట్రిక్ ఫీల్డ్ ఇంటెన్సిటీ ఆర్ ఫోర్స్ ని ఏ విధంగా క్యాలిక్యులేట్ చేయాలి అని మనకి క్వశ్చన్స్ అడగొచ్చు, రైట్? ప్రాబ్లమ్స్ ఏమి ఇవ్వరు. Only the question will be asked to derive, right? To derive the expression for E bar or derive the expression for F bar for some special charges that we have already studied, like infinite line charge gani, infinite sheet of charge gani, like with a spherical sheet of spherical charge manamu ring edaithe chadivamo, these three things. So the question might be asked about these three things. Okay, so that is one. Or they can ask you to find out for any subject, for any kind of charge, right? Okay, charge chesi daniki E bar gani లేదా F bar gani determine చేయమని అడగొచ్చు. Okay, so what is the general procedure అనేది తెలియాలి. That is the first topic, right? So that we will discuss today, right? The second topic will be divergence. Okay, that we will see later on if the time permits. Okay, so a quick recap of what we have discussed till now, right? And then we will okay, we'll go to the application of Gauss law and we'll stop by that. Okay, so what is a quick recap is so first thing, limitations of Coulombs law. There are two limitations. Coulombs law can be applied only to point charges. It cannot be applied to line charges or surface charges. That is a point one. Second is when there is a combination of multiple charges, we cannot apply Coulombs law. Okay, so there are limitations. So to overcome that, we are going for the next type of method to calculate the electric field intensity, and that is the concept of electric flux and Gauss law, right? So what is electric flux means? It is the number of lines that are passing through or that are coming out of the things. So flux line means it is a force line, imaginary force line produced by a charge particle. The total number of lines produced is what we call it as the flux of the charge, and the number of flux lines that are present inside in a closed surface is what we call it as flux density. Okay, and then we have seen what is a Gaussian surface as well, right? Now the next topic, which is about the application of Gauss law to determine, right, E bar or F bar. Okay, so there are 5 steps for this. This is a very important topic, as I said, the most important from this part, because we'll get a question on this, right? So how to apply Gauss law? Okay, to find out, to determine E bar or F bar. The first step is we have to choose the Gaussian surface, right? Choose the Gaussian surface, right, as per the require as per the structure of the Gaussian surface, as per the structure of the charge particle, right? And the charge particle, you don't know what exactly the charge is, but there will be some structure, right? Some structure of the charge. Okay, so let's say there is some closed structure like this, or there is some line structure or a rectangular structure, anything regular. So whatever that is close to this, we have to choose that particular surface. Okay, this is the first thing, right? So choose the Gaussian surface, right? Choose the Gaussian surface that matches with the structure of the charge particle. Okay, this is the first point. The second point is, right, after you choose the charge particle, after you choose the Gaussian surface, then take the coordinate system, right? Consider the coordinate system that matches with this Gaussian surface. Okay, coordinate system, consider the coordinate system that matches with the whatever the Gaussian surface you have taken. For example, if I've considered a cylindrical surface, then obviously my choice will be cylinder. Okay, I've considered a line. For example, my charge looks like a line. So in that case, I have to consider cylindrical itself, right? For example, if my charge particle looks like a sphere, so I'll go with spherical surface like this, right? Whatever it is. Okay, so whatever the Gaussian surface you have considered, so choose the coordinate system that matches with this Gaussian surface. Okay, that's the second point, right? So after that, once we choose, then we have to write down the values of d bar and ds bar. Okay. What is this? For example, let us assume that a simple example, I have considered my charged body to be a box nature. So therefore, definitely for this box nature, right? For this box nature, so I will consider a Cartesian coordinate system, right? So I will consider a Cartesian coordinate system, because that will my Gaussian surface will be a box, right? My Gaussian surface will be a box. So therefore, obviously, right, I will choose a Cartesian coordinate system. Okay. So again, what we have to do is, we have to remember is, we have to calculate. How do we calculate flux density? How can we calculate flux density? Flux density, if I want to calculate, then the surface, I have to consider a surface which is normal to this flux lines. Understood? Okay, Nama. So, ante whenever you want to calculate the flux density, so manam em cheyali, we have to consider a flux a surface that is normal ga unna teesukovali. Okay. So first ఏంటంటే, first I have considered, right, a box, right, as my Gaussian surface. Then the coordinate system I have considered is a Cartesian coordinate system. So I have to write d bar in the Cartesian coordinate system. What is a d bar in Cartesian coordinate system? So it is, obviously we can write it as dx ax. Let's say the component along x-axis is dx and the unit vector is ax, dy ay, and dz az. Okay, so these are my this is my flux density. Okay, so dx ax, dy ay, dz az. Okay, similarly, right? Okay, similarly, ds bar is what it is. It's a surface change, right? So the area, surface area, right? Now here the point we have to make is, this d bar we have to calculate. The d bar have to be calculated along one particular direction that is normal to the, right, charged body, or that is normal to the surface. Okay, for example, if this is my, right, charged particle, let's say this is my charged particle, then the box will be like this, surrounded over in all right directions. Okay, but I cannot calculate, if I want to calculate flux density, I cannot take this direction because it is not normal, right? This direction, okay, that is the I cannot take top or bottom, I cannot take side, right? Normal means it has to be like this. So let us assume we can take this also, right? This is also okay. So anything, let us consider that our Gaussian surface, I am placing it like this. Understood? So this is my charged body, I am placing the Gaussian surface like this. Okay, like this. This is the surface. So I am going to calculate what are the flux lines that are coming out of this, and I will calculate the d bar. Understood? So let us assume that dy ay, that is the y component. Y is the plane. Y plane is the plane which is normal to the thing. So d bar will have only a component along y, and rest of the components we can eliminate. Understood, ma? So I'll repeat it again. See again, what I'm saying is, first we have to consider a Gaussian surface. Okay. So choose a Gaussian surface. We have chosen, right? Let us say I have chosen as a box, right? And for a box, the system that matches is obviously Cartesian coordinate system. Okay. Let us say this is a Cartesian coordinate system. Okay. So next is, whenever I want to calculate d bar, in general, the expression for d bar will be dx ax plus dy ay plus dz az. Okay. So this is the general expression. But out of this, right, out of this things, right, the d bar we can calculate only along one direction. అంతే కదా, ఒక డైరెక్షన్ లోనే క్యాలిక్యులేట్ చేయాలి d bar అనేది. We cannot calculate in all three directions. Only normal direction లో క్యాలిక్యులేట్ చేయాలి. Let us assume the normal direction in this case is dy ay. Okay. So let us assume the direction normal to the surface is dy ay అనుకుందాం. So ఇది right, this will be d bar. Okay. D bar will be equal to dy ay, and now, right, now what is the ds bar? Ds bar along y we have to consider, ante kada, normal. So then only this surface will become Gaussian surface. Ante normal అవ్వాలి అంటే ఖచ్చితంగా మనం ఏదైతే సర్ఫేస్ ఏరియా తీసుకుంటున్నామో అది కూడా సేమ్ డైరెక్షన్ లో తీసుకోవాలి, రైట్? సింపుల్ పాయింట్. ఇది ఎక్కడ ఏ డైరెక్షన్ లో తీసుకున్నామో this also have to be taken in same direction. So as we have already studied, the surface area change along y can be written as dx dy dz ay. Okay. So this is the third step, right? Most important. Okay. So till now, right, first is we have to choose the Gaussian surface. Second, so as per the Gaussian surface, choose a coordinate system that matches with this. Then after doing that, identify the normal plane. Identify the normal plane, right? Normal plane has to be identified, and for this normal plane, what is the d bar and what is the ds bar, you have to write down. Okay. After this, right, once we do that, once we write all these things, right, next thing is, after finding out d bar, and so just take the dot product of d bar dot ds bar. Okay. Take the dot product of d bar and ds bar. So here we can observe that both d bar and ds bar will be in same direction. Okay. రెండు ఒకే డైరెక్షన్ లో ఉంటాయి, ay dot ay. So ay dot ay will become 1, right? So d bar dot ds bar will be equal to, right, dy dx dz. Understand? So this is the fourth step. So take the dot product of d bar dot ds bar. Okay. Right, take the dot product of d bar and ds bar, and then the fifth step will be, and then the next in this step itself, so take the integral of d bar dot ds bar. Take the integral of d bar dot ds bar. So that is integral of dy dx dz. Okay. So this is a surface integral, ante kada. Surface integral ante there will be two integrals, right? So dy is the required value, that is what we want, right? So this will be along x, along z, dx dz. So we can calculate, we know the limits of x, right? So what is the right length of this box you have considered, right? Okay. And what is the height of the box you have considered? This is x, this is z. So you know the limits of x and z. You substitute the limits substitute cheste, we'll get, right, like this. Now as per, right, thing, we know that integral d bar dot ds bar will be nothing but psi. Will be nothing but psi. So this is basically psi is equal to dy into integral, right, x integral z dx dz. Okay. So again, the psi is nothing but, from Gauss law we can write psi as nothing but q. Q is equal to this thing. So from this we can write dy is equal to q divided by, right, whatever you get, x z, right, dx dz. So this is how I can calculate dy. Okay. So if I calculate the flux density, it will be easy to calculate E bar. Okay, how is that? We will see in the next class. Okay, so these are the steps, right? I will repeat the steps again, right, for those who have missed or who are not clear. So let us repeat the steps again, and we'll stop for today. Okay, so there are total 5 steps. The first thing is whatever is the type of charge that is present, whatever is the type of charge present, based on the structure of the charge, choose a Gaussian surface. Okay, so that charge that might not be a perfect match, but looks closer to it. Okay, after choosing the Gaussian surface, I have chosen the Gaussian surface. Now choose a coordinate system that looks near to or that is similar to that of this Gaussian surface. Okay, so this Gaussian surface, right? So once we do that, right, obviously what we get is we will right once I get a surface charge, right? Sorry, once I choose a coordinate system, then the next step will be I have to write the d bar vector, right? Identify the normal plane, right? And in this normal plane, what is the d bar and what is the ds bar? Write the general expressions. Once you write d bar and ds bar, right, if those two are done, right, take the dot product d bar dot ds bar and take the integration of this. Okay, so integral d bar dot ds bar I'll get. Okay, now, right, this d bar dot ds bar flux density into area is basically flux psi. Okay, so this will be the expression, right? Now after this, the Gauss law. What does the Gauss law say? Gauss law says that the flux will be equal to charge, right? So I can calculate the charge from this. Okay, right? Or I can write like this. Now what is the unknown for us? Unknown for us is the flux density. If we calculate flux density, we can calculate electric field intensity. How can we calculate electric field intensity? E bar will be equal to epsilon into d bar, right? So this sorry, E bar is, sorry, d bar is equal to epsilon E bar, right? So this derivation we'll do in the next class, right? We'll continue next class from this, right? So once we calculate dy, that is d bar, I can calculate E bar. Okay, electric field intensity, right? So all these things, right, we will take an example tomorrow, right? Because the time is completed, so I'm stopping the class for today, right? Tomorrow we will see how these 5 steps are to be applied for I'll take 2 examples, infinite line charge and spherical charge, and see how we can apply Gauss law and all, right? So this is today's session. So today we have covered the limitations of Coulombs law, flux density, Gauss law, and how to apply Gauss law for calculating d bar and d bar. In the next class, we will definitely see how to apply them with the help of examples and do the problems. Okay, right. I think I'm reaching to you. So if you have any doubts or if you are unclear about anything, you can just ask me, right, in the chat box, or shall I unmute and you can ask? Is it is better to ask in the repeat third point video stopped? Okay, okay. Is the video coming now? Shall I again yeah, shall I repeat it again? Okay, I think I'm clear, right? Any doubts till now? Why can't we consider tangential and normal both, sir? Okay, we can consider tangential or normal, not both, right? So we have to consider that is flux density will be calculated per surface area. If we consider both and tangential and normal, then it will become like this, something like this. This will not be surface area. How can I say it is a surface? The surface area or the volume అయిపోతుంది, right? Surface area under 2 dimensions. Yes, ds kada manaki. We have to integrate it with respect to ds dot ds. Ds means